Good morning, everyone. Happy Tuesday. Today's a big day. Today is probably the last day of classes for our stats course. We will probably get through the last of the material today and have a little bit of time at the end of the class today to chat about any questions you might have regarding the data collection assignment. Jordan, if you wanted to stay after class is over or after the material's done, I do want to talk a little bit about your data. And if you want to actually just prepare for that chat, I just want to see your data again, because I got your email and I was looking at it this morning and I want to respond back to it in a way that makes sense, but I'm going to need to see your data to do that.
Awesome, thanks, Brian.
Yeah, no worries. So the last thing I would like to cover, and let's just get through the material just so we're done. The last thing I want to show you is how to perform a confidence interval or a hypothesis test if you happen to be working with numerical data. And the numerical data essentially has two pieces of information, kind of two populations that you're working with. So this is a two mean kind of scenario rather than a singular mean kind of scenario. So very similar to what we were doing with proportions, where you have kind of this target population, you have these two subpopulations, and you've gone and collected data on those two subpopulations, and you want to make a comparison between the two. It's the same kind of thing here. You have the target population with your two subpopulations, only that it's numerical data. So those two subpopulations, not only do they have a mean, mu, but they also have standard deviations. And when we were looking at the last time we were looking at working with means, we kind of went through this discussion about how we don't normally know the target population's standard deviations. So we usually have to estimate them based on our data. And we have to do something similar here. And that essentially results in us having to use the student t distribution rather than the standard normal distribution. So a very similar thing is going to happen here. We're going to set it up very similarly to our difference of two proportions. We're going to go collect our data. We're going to assume that there's no difference between these two subpopulations that we've collected. So we end up with an estimate that is the first mean minus the second mean. So that's what we're going to be taking as essentially our point estimate for the measure of center of the difference between these two subpopulations. And that's going to lead us to a sampling distribution that looks something like this. So provided that we satisfy the conditions for the central limit theorem, we're going to have a roughly symmetric distribution that's going to look roughly normalized as well. The mean of that sampling distribution is going to be the true target means, the difference between those two. So mu1 minus mu2, those are from the two target subpopulations. And then we have a standard deviation, which we call the standard error, that looks like the following square root. So it's going to look very similar to the singular standard error, which was, I believe, it was just sigma over square root n. So in this case, we kind of just have to add in that secondary subpopulation standard deviation to get an updated standard error. So this is going to kind of measure the spread for us for our sampling distribution. And what's going to happen is we're going to kind of roll into a hypothesis test, assuming that there is no difference. So our assumption is always going to be that the difference between these two subpopulations is 0. And then we're going to go and gather evidence to see if we feel like that is still valid or if we think that the difference might be something else. And like I was saying, with regards to a singular mean, is we often don't know what the standard deviation is. So what we're going to be doing when we work with our confidence intervals and when we work with our hypothesis test is we're going to be estimating the true target standard deviations by using the populations, the sample population standard deviation. So this is represented by S1 and S2. So it might be worthwhile for us to kind of step back. I'm going to show you and compare it to how we kind of thought about our two subpopulations for proportions. And we'll see kind of how the setup is quite similar. The only difference is we don't really have to calculate a pooled value anymore. But we do have to estimate the we have to estimate the standard deviations. So this was what we had chatted about with regards to two proportions. And just let me kind of erase some stuff and make sure that I'm sharing the right screen here. So yeah, so you guys should be able to see that. So when it came down to two proportions, it always comes down to thinking about what the target is, what's happening in the target and what's happening in the sample or in the data that you collected. For two proportions, we had P1 and P2. We had our two subsamples. Those were our two target proportions. When I go to collect the data, again, I have these two subsamples and I estimate what I think the target proportions are based on the data. And with two proportions, since we didn't know P1 and P2, we estimated this pooled number and then used the pooled number essentially to get a better estimate for the standard error. Now with regards, so this is the proportion idea. So let me just proportions. And so let's talk about what happens with respect to averages or with respect to dealing with numerical data instead. With numerical data, you still have target and sample population, and we still have our two subpopulations. So this could be, to keep it maybe nice and easy, let's just think males versus females, right? That's usually an easy kind of two subpopulations that are easy for us to kind of think about. So let's say, number one and number two are males and females. And each subpopulation is going to come with a target measure of center, which we call mu1 and mu2. And each target population also comes with a standard deviation. Now, inside the sample, when we go to collect our data, we have decided, for one reason or another, to stratify this data or to kind of separate out these subcategories for our piece of numerical data. And we collect the data and we can create some estimates that we think are good guesses based on our data to represent these four parameters we have for the target. So for our subpopulations, this usually comes down to using the averages to estimate the means. So we call that X1 bar and X2 bar. And then we use the sample populations to estimate the standard deviations as well. So we call this S1 and S2. So this would be very similar to what we called SX. This is going to be the SX button essentially on our calculator. So for those of you that are working solely with numerical data, you can just use Microsoft Excel. You're going to use the sdev.s command, I believe. So we want to do the standard deviation based on the sample, not based on the entire population. And because we don't typically know, sorry about all the calculus stuff down here at the bottom. Since we don't typically know the target sigmas, we don't typically know these standard deviations, the S1 and S2 become our best estimate. And we can do this at the expense of using the t-distribution rather than a standard normal distribution. So it's kind of like, I don't know if you're like anime fans, but it's kind of like Full Metal Alchemist. It's like equivalent exchange. You can give up one thing at the expense of having to do something else. So that's the breakdown. That's the key differences I would consider between using proportions and using means. Set up in a very similar way with our two subpopulations, only that the numerical data has those extra parameters that we need, sigma 1 and sigma 2. We estimate those using the data that we have to get S1 and S2, and then that allows us to utilize the student t-distribution. So as we pop back into the notes, what you'll notice is that up here, we talk about the sampling distribution having this particular mean and this particular standard error. If we happened to know sigma 1 and sigma 2, we could use the normal distribution. This is going to be a normal sample distribution, but we don't know sigma 1 and sigma 2. So we alter our formulas. For example, the formula for the confidence interval, we take a standard error where we use the estimate S1 and S2 in place of sigma 1 and sigma 2. And then we have to utilize the student t distribution. So you're going to see a t cutoff number here rather than a z cutoff number. And it'll be similar when we go to do our hypothesis test as well. When we go to find our t star number, we're going to use the standard error of the sampling distribution, that our best guess of the standard error. And again, because we're using an estimate, in this case, we do have to utilize the student t distribution. So here's our formula for creating a confidence interval. And you might remember that when dealing with the student t distribution, we had a whole bunch of different rows that all correspond to the degrees of freedom our distribution has. So every t distribution depends on how much data we've actually collected. So we need to have a way to figure out what row to use inside of our chart. And the easiest way to do that is to not overstep our welcome and to take the smallest of the two numbers, n1 minus 1 and n2 minus 1. So n1 and n2 represent the sample sizes of our two subpopulations of data that we've collected. We subtract 1, and then we'll take the smaller of those two numbers. And by taking the smaller of those two numbers, we essentially don't take more probability than we should when we're gathering our evidence. So that's the reason here, or the reasoning for utilizing this particular approach. It's essentially not to take more probability than we should based on the data that we've collected. And so the final slide here that I just flashed a little bit earlier goes through the process of actually setting up and executing the hypothesis testing procedure. I think we should just jump right into the example. I'll show you how to construct a confidence interval, and I'm going to show you how to set up and execute a hypothesis test using a probability number as well. So I'm going to grab this example. I'm going to pop over into OneNote, and we're going to start interpreting the values here and see if we can get at part 1 and part 2. So I'll show you how to do it in both ways. And like I've been saying, typically the probability value is typically the way that we go with regards to hypothesis tests. Okay, so we are in a school district and we have 30 students are assigned to group 1. Group 1 we're going to call Mrs. Smith. 25 students are assigned to Mr. Jones. We're going to call that group 2. At the end of the year, the classes take a standardized test. So we're going to assume that that standardized test looks the same for all students and that the scores of the test are summarized below. Okay, so we're taking Smith as group 1. If I could spell group, that would be great. And Jones is group 2. So that means that 30 we're going to take as N1, 25 we'll take as N2. So these are the sample sizes that are associated with the two groups. We have averages. So these are the average score on the standardized test. So we can take these to be our X bar 1 and X bar 2. And then we have the associated standard deviations of these tests as well. So we're going to take 10 and 15 to be our S1 and S2. And what we're going to do is we're going to first try to construct a 95% confidence interval to try to figure out whether or not we believe there is a difference between these two groups. And then we'll go ahead and we'll set up a true hypothesis test and try to calculate a probability number to make this work for us. Now, first, what we want to do before we start is probably check the conditions. So let's go ahead, let's do maybe a quick condition check because we've really already sorted our data. So typically when you come to an example on, like when we come to the example on the final exam, all of the information is already going to be sorted into your two subgroups. So we don't really need to go through that process like we did in some of the other questions where we try to sort stuff out because it's mostly going to be sorted out for us anyway. So I've already labeled everything, everything's sorted. So I'm going to jump right into the conditions. Now this condition check should work for both part 1 and part 2. And remember, there are typically two things that we need to look for. We need to look for the independence condition and the sample size condition. And those things do vary a little bit depending on whether or not you're working with categorical or numerical data. So let's check the independence condition. With categorical data, that would be the less than 10%. For numerical data, we're really just looking to see if we have a simple random sample, right? Is there some randomization involved in this particular study? And it looks like there is a little bit of randomization involved here. We randomly assigned our students to the two groups. Okay, so there is random assignment. That's probably good enough for the independence condition here. All right, and next up, we want to look at our subgroups and just make sure we have large enough sample sizes. Now, remember, for numerical data, we're typically looking to have 30 or more inside of our samples. For categorical data, a little bit different. You're looking for the 10-10 criterion, the 10 successes, 10 failures to ensure that you have enough data. Sample size, well, I mean, one of the groups is 30, one of the groups is 25. So, I mean, provided the scores are roughly symmetric, I'm not going to, put up too much of a fuss, but that one group is a little bit smaller than I'd like to see. So I might want to do a histogram just to kind of check to make sure that scores are roughly symmetric. But let's assume that the scores are roughly symmetric so that we can use the student t-distribution. So we do have N1 is greater than or equal to 30. So that's good. But N2 is less than 30. So we will have to make an assumption that the scores here are roughly symmetric. So with that assumption, the CLT would work. And then we know that our sampling distribution is going to be a student t-distribution. And we know that this is going to look a little bit weird, but the center of our student t-distribution is going to be mu1 minus mu2. So it's going to be the difference between our two target means. And we know that the measure of spread, and we know the measure of spread of this student t-distribution is going to be the estimate. I should actually not use, I should use SE. So the standard error of our student t-distribution is going to be roughly S1 squared over N1 plus S2 squared over N2, all under a square root. Now, the last bit of information we're going to need to talk about our student t-distribution is the degrees of freedom. We're going to take N1 and N2 and subtract 1. So N1 is 30. Let's subtract 1, we get 29. N2 is 25. And by subtracting 1, we get 24. So the minimum, or the smallest of these two numbers, is 24. So the degrees of freedom, or the row that we're going to use for the student t-distribution, is going to be 24. Okay, so that's the basic setup. So, I mean, the condition check is not that much different from a single mean. We just have to check each of those two subgroups separately. So I think with that said, let's go ahead and try to set up a confidence interval. And we're going to try to interpret that confidence interval with respect to whether or not we think there's a difference between these two groups or not. So let's do part 1, which is a 95% confidence interval. And a 95% confidence interval should have the form x1 bar minus x2 bar. So we're going to calculate that. And then we're going to add and subtract some cutoff number from the student t table times the standard error, which is given by that awful square root. Now, what we should probably do is head over to the t-distribution and find this first, because we really have all the other bits of information that we need. I know x1, I know x2, and I know the s's, and I know the n's. So the only thing we're really missing is this t star number from the table. So how do I get this? Well, we need to go to row 24, and we need to scroll along the top, and we need to find the 95% CI. All right, so let's boot over to our T table. We're going to scan along row 24 and find the intersection of row 24 with the 95% column. So there's a column up here that says 95%. We'll scroll down. So we're going to take 2.064 as our value. Okay, so the intersection of row 24 with the 95% column. Now that we have that value, we can input all the rest of the values and try to actually get this confidence interval. So I'm just going to scroll back in my actual packet here just to get those numbers. So we had x1. I kind of want to take x2 minus x1. Not that it really matters. Let's just take x1 minus x2. I kind of wanted to take the bigger number minus the smaller number, but it doesn't, in the long run, it doesn't really matter. There's going to be symmetry in the interval anyway. So let's take the mean score 78, subtract the mean score of 85. And the reason I wanted just to be a little careful is because we're going to get a negative number here. And I kind of wanted this number to be positive, but it should still work out either way. We're going to get to the kind of mirror image of what we want here. And I'll explain that when we get there. So we'll multiply by our multiplier, 2.064. And our S1 is 10 and S2 is 15. So we're going to get S1, so we're going to get 10 squared over 30 plus 15 squared over 25. And then it just becomes a little bit of a calculator game. So I'm going to load up my calculator, and you'll hear some frantic clicking as I start inputting things into the calculator. And it's probably easiest if I just share my screen, I think, at this moment in time. Okay. One thing that's kind of annoying about Zoom is that I don't have enough space to do stuff. So maybe over here. Hopefully that doesn't block too much on you. So 78 minus 85. Let's just get that number. This is -7. So I'm going to toss that in here. So we have -7 plus or minus some stuff. My preference is usually to try to input all of this as best as I can, because the calculator can handle inputting all of this stuff. So let's go -7. Let's do the subtraction first. So 2.064 times the square root. Under the square root, we're going to have a fraction plus a fraction. 10 squared is 100. 30. And I don't know what 15 squared is off the top of my head. So 15 squared over 25. That should do the trick. I think that's going to be what we need. -7 minus the thing. Yep, boom. -14.24. And we will rinse, lather, and repeat for our second value, which is going to be -7. I'm going to go back, just delete and change that to a plus sign. And this should be our upper value, which is 0.25, let's say, or 0.24. Was the other one 2.5 as well? Did I round that incorrectly? Yeah, this should be a 2.5 as well. So if I'm going to go with the 2 decimal places, which I think is pretty standard for numerical data, if this was categorical data and I was working with proportions, I probably would round these to 4 decimal places in case I needed to convert these to percentages. But since these represent essentially our mean score, I can leave these rounded to 2 decimal places. So we get the following interval. So how do I interpret this interval? I interpret this interval as 95% of the time, I do expect the difference of the 2 averages to fall between -14.25 and 0.25. And remember, we're talking about the true target population. So we use our estimates, we create this interval, and this is like an expected interval where we do expect the true target population to fall. Now, let's look at this interval in a little bit more depth. It's weird that we're getting negative numbers, but this is life when we're dealing with difference of 2 proportion or difference of 2 means. So we get a -14.25. We have a 0.25 as our upper bound. And what we're curious about, if we believe that there's no difference between these 2 subgroups, I would expect 0 to fall on this interval. So just like we were doing with 2 proportions, we're looking at the bounds of our interval and we're going to compare it with the number 0. And the number 0 is going to be pretty close to this kind of upper bound of 0.25. And so we have to kind of make a judgment call here. Essentially, what we probably would do is we probably would say, since 0 lands inside the interval, there's some evidence to suggest that there is no difference between these 2 subgroups. So essentially what we're doing is we're wondering if there's a difference. So we assume that there is no difference, or we assume that the difference between these two subgroups is 0. If 0 lands on this interval, which it does, we have evidence to suggest that there is no difference between our two groups. So since zero lands on our interval, we have some evidence to suggest there is no difference between our two subgroups. That is, if I go back and I look at what I was initially comparing, we're actually comparing the standardized test scores between the two teachers. So there's some evidence here to suggest that the test scores that we're seeing are similar. Or in other words, we haven't really been able to find enough evidence to suggest otherwise. So if our assumption is that there's no difference, we don't really have enough evidence to suggest that these test scores are really that different from each other. If you were to go and create side-by-side box plots of these, can we do that? Let's see, we have we can make side-by-side box plots. The essentially kind of like the IQR whiskers should overlap each other, should overlap the kind of the centermost points of our box plot. So if we were to put kind of error bars on a histogram or error bars on a box plot, we should be essentially overlapping the important measurements on those visuals. So if you do read some more scientific papers, that's typically what happens. They'll kind of have this visual, they'll have the error bars, and there's going to be an overlap inside the error bars on the picture. So that's kind of a way to connect it back to what we were doing at the very start of our course. So that's how to set up and execute a confidence interval, very similar to your difference of two proportions, right? So we kind of set it up, execute it, check to see if 0's on the interval. If it is, we don't have evidence. If 0's outside the interval, we do have evidence to suggest that there is a difference. So how does that feel? Do you guys feel okay with that? It's just really a matter of learning the new formulas, I think. The procedure is very, very similar. But just let me know if you have any questions about the setup. Cool, I got a couple thumbs up. That's good. That's good. All right, so let's jump back into the question again. We're going to actually perform the hypothesis test. So how would the hypothesis test look slightly different compared to setting up and executing a confidence interval? So we've already checked the conditions. We don't need to check the conditions again, but normally to start off your hypothesis test, you would want to check the conditions and make sure you can actually utilize the student t distribution. So I'm going to skip over that. We're going to start right with actually stating our two hypotheses, the null hypothesis and what we believe to be the alternative. So for the null hypothesis, remember that we're rolling with there is no difference between the two subgroups. So we assume that they are the same, essentially. So we essentially assume that the two subgroups are the same. And then when we simplify this expression, we get the following. We get that mu1 minus mu2 is equal to 0. Okay, so that's always our assumption. That's always our null hypothesis, is that there's no difference between these two groups. They're actually essentially the same. That means our alternative is going to be a two-sided kind of test because we're going to use the not equals to sign here. We're going to assume that there's no difference and then try to collect some evidence to show that there is a difference between the two groups. Notice that if we were to kind of simplify this, we would get mu1 not equal to mu2. There is a difference between these two means. So that's always the alternative. There is a difference between our two subgroups. All righty. So if we were to actually go back to our notes and kind of flip back to some of the stuff that we need to do. So this will be page 6 of your packet. So we've specified the null and alternative hypothesis. If necessary, we need to compute some statistics. So we do need to compute T star. That's going to be the important one. We already know x1 minus x2 is going to be -7, but let's go ahead and compute the standard T star and the standard error. So we're going to compute the T star statistic. Okay, so T star is given as the difference of our two samples, x1 bar minus x2 bar. That's the numerator. The denominator is the standard error. And you know me, I typically like to try to get as much accuracy as possible. So I'm going to actually put that whole standard error into the denominator and just have my calculator take care of trying to get that as accurate as I can. And I'm going to try to get this accurate to 3 decimal places so we can kind of compare this to row 24 of our T distribution. So when I go to utilize my calculator, I'm going to be inputting the following. So we have, let's see, we have 78 minus 85 over some stuff. So I'm going to go ahead, I'm just going to share my screen and pull up the calculator so that we can input this awful fraction in place. So let's see, 78 minus 85 and into the denominator. We have 10 squared over 30 and 15 squared over 25. Okay, this is nice. It fits on one screen. I can see that it's all programmed in correctly. Let's throw down an equals, and it's going to give me this. If I press the SD button, if your calculator is not set up to show decimals automatically, the S to D button will convert from the fraction to a decimal. So we're getting something like -1.99. So I'm just going to write that down. Let's go 1.993. So -1.993. Now, if we go over to our T chart, you're going to notice that there are no negative values inside of the T chart. All of the T distribution cutoff numbers come as positive numbers, and that's because the distribution is symmetric about the origin. So we're taking the measure, the middle number to be 0. We calculated a negative T star, but we're just going to take that to be positive because of symmetry. So the idea now is to understand that we're working with the T distribution with 24 degrees of freedom. We're going to scan along row 24 and try to get as close as we can to 1.993. So let's scan along row 24, right? That's how many degrees of freedom we had. and try to get as close as we can to 1.993. All right, row 24. We're going to scan along and get as close as we can to 1.993. So it's going to be somewhere in between what I've highlighted here, 1.771 and 2.064. So typically what we do is if we are kind of in between two things, we're going to go back and we're going to take more probability rather than less probability. We never want to overstep our bounds. So 1.711 is as close as we can get without going over 1.99. So once I have as close as I can get, I'm going to scroll down, go to my two-sided probability, and we're going to take 10% as our probability value. Now, we don't want to take 5% because that would be overstepping our bounds because we've gone over 1.993. But if you decided to kind of come back at me with a probability number that's somewhere in between these two, like 8% or something like that, that would be fine. I would be okay with that. But we just can't overstep and go all the way to 5%. So what we typically do in our stats course is just take a little bit more probability just to make sure we don't overstep our conclusion. So we're going to take the two-sided probability number of 10%. So what do we land on 1.711 and scroll down to our two-sided P. And get 10%. So we're going to utilize this probability number to try to figure out what's happening. And if you do want a picture to kind of go along with this calculation, we have something that looks like this. Here in the middle, we have our mu1 minus mu2, which is 0. So this is our sampling distribution. We calculated a cutoff number. I apologize. We calculated a t-star 1.993. So we had cutoff numbers here and here. And we're curious about how much probability lies inside of these tails. Okay, so we're calculating the probability of getting a measurement of -7 or more extreme. And that's 10%. Okay, so that's if you want to know what the interpretation of this probability number is, it's essentially giving us the odds that we see a difference that's similar to -7 or more extreme, and that's 10%. I would say 10% really isn't small enough for us to warrant any concern. I would say that 10% probably does not give us enough evidence to suggest that there's a difference between these two subgroups. Remember that typically the gold standard is usually 5% is what we're trying to compare to. So since a P is 10%, which is larger than 5%, we would typically say there's not enough evidence to warrant rejecting the null hypothesis. So in other words, based on the data, based on this probability number, it's really likely that the difference of the scores of these two classes It's really just random variation. It's not really too extreme that I should be concerned. Or in other words, these teachers both did an equally as good a job as they could based on the scenario that's happening in the world today in the pandemic, and the students did relatively okay. They're relatively the same. Good old pandemic learning. So that's really all I would like to cover with regards to working with two means. That's really what you guys need to know for the final exam. The rest of the packet here is something that we normally would cover if we needed to do ANOVA by hand, or we needed to discuss ANOVA. But we discussed the ANOVA test actually in the lab. So all of you would have been exposed to at least a little bit of the theory with regards to ANOVA by some of the reading in the lab and some of the reading that would have been asked on the textbook. So the section of the notes here on ANOVA, which would be kind of everything after this example, will not be covered on the final exam because we've already tested you on that with regards to the lab. So my preference, because we're kind of getting close and I want to spend a little bit of time today and tomorrow helping students out with their data collection assignment, is I'm going to not cover the topic of ANOVA because it's already been tested on the lab. That's going to give us a little bit of extra time today for those of you that do want to stick around and ask questions with regards to your data collection assignment. Yeah, so that is class for today. I'm actually